So we've been talking a lot about reactions that have reached equilibrium. But what about a reaction that will eventually reach equilibrium, but it hasn't yet? How do we evaluate what's going on inside that reaction vessel? Well, now we can talk about this new concept called the reaction quotient, or Q. So what this means is that you have some generic reaction, and we'll go ahead and just use our generic reactants and products of A and B as our reactants and C and D as our products. And the reaction quotient, we still write it very similarly as we do for the equilibrium expression, but we can write this and fill it out for any sort of conditions. So what I mean by that is Q is not constant. So we could write the reaction expression and get some value for Q at any concentration of reactants or products. You can get a different value for Q. Now, if this were the equilibrium expression, then these concentrations would have to be the concentrations at equilibrium for this reaction here. But since we are using Q now, these do not have to be the equilibrium concentrations. So let's take a look at a specific example. So we've got N2O4, and it's decomposing to 2 moles of NO2. So our K value is 4.65 times 10 to the minus third. Okay, so we can write Q is equal to, it's our products, and then we have to raise it to 2 because we've got that the coefficient, the stoichiometric coefficient is 2, so it's just the same. We do it the same way, and we've got our reactant in the denominator. So what you can do is imagine a scenario where you conduct experiments and you start each experiment with different ratios of reactant and product. Okay, so if this were at equilibrium, Q would be equal to K. So Q equals K at equilibrium. So let's think about how Q is related to K when a reaction is not at equilibrium. So here we have our example, and in this scenario we have run 3 different experiments. So these are 3 separate experiments, okay? And each time we have started off with a different concentration of product and a different concentration of reactant. So let's look at experiment 1. So in experiment 1, we have no product. So our Q is 0 squared over 0.04. So that means our Q value is 0. So one conclusion we can draw about the relationship between Q and K is that when there are no products present, Q is 0. In our next experiment, we have no reactants. So you can imagine that in this scenario, the reaction has gone to completion. So we don't usually see this with equilibrium reactions because we don't use up all of our reactant. But if that were to be the case, then that means that we would be dividing by 0. So it would be 0.06 squared divided by 0. And that is not something we can do. So we can't define that when we only have product. So if we have no reactant, Q is irrational or undefined or infinite. So we can't really use Q to define a reaction that has gone to completion, which makes sense because this is really about having both species present, and if it's not an equilibrium reaction, we don't really need to think about Q. Now we're at our third scenario here, where we have some product formed and we still have some reactant left. So if we were to write our Q for this, it would be 0.02 squared divided by 0.06, and we get 6.67 times 10 to the negative 3. So let's compare that to our K value. Our K value for this reaction is 4.65 times 10 to the negative 3. So Q can have any value from 0 to infinity, which would be the undefined value. So it can be greater than, less than, or equal to K. Okay, so here we see that it is greater than K, infinite, less than K, 0. And here we see that this is actually also greater than K. Okay, but remember we also stated that when Q equals K, the reaction is at equilibrium. So let's look at our scenario right here. We see that our K value is smaller than our Q value. So that should tell you which direction the reaction is going to go. So let's visualize this with kind of a number line. So in this scenario, I have two options. So we can place Q as either to be less than K or greater than K. So here's our K value, 4.65 times 10 to the minus 3. Okay, so let's take a look at what happens if Q is smaller than K. So here's our Q value. Okay, so remember the idea is that at equilibrium, Q is equal to K. So that means that the reaction is going to move in the direction to make Q and K equal, because that's what's driving this, right? The reaction proceeds until those reactants and products are in that correct ratio. And so we know that Q is going to move in the direction of K. So that means that we are going to go like this. Okay, so we would say that this reaction proceeds to the right. Another way of saying it, we have too much reactant and not enough product. So more product is going to form. Or you could say that the forward reaction is favored because we're moving in that direction toward product. Okay, so now let's imagine that Q is greater than K. So we'll put Q over here. And again, Q is always, or the reaction's always going to go toward K. That is the driving force of this reaction. So that means the reaction proceeds to the left. So reactants need to form, or product needs to break down. Okay. Or you could say that the reverse reaction is favored. So let's go back to our example here. So in the way that we have written this, the reactant is the dinitrogen tetroxide, and the product is nitrogen dioxide. So in this scenario, for these two values, our Q value is greater than our K. That means that we have too much NO2, and the reaction is going to go in this direction. So we would say that in order for equilibrium to be reached, we need more N2O4 to reach equilibrium. So let's do another practice problem. So in this reaction, we've got iodine gas and chlorine gas reacting to form iodine chlorine gas, I guess, 2 moles of this. So our equilibrium, and I've given this to you in pressure. So remember, Kp just means that pressures for gases. So Kp is related to the concentration by the ideal gas constant. So just be aware that you're paying attention to what units we're using. So our K value for this reaction is 81.9, and these are our pressures. So how do we evaluate what is Q and what is the direction of the reaction? So we can set up our equilibrium expression or our reaction quotient expression. So we've got Q, and we know that we have to put the pressure of the iodine chlorine gas, or iodide chloride, I guess, I don't know, funnily enough, and that's squared. And then we do the pressures of our iodine and chlorine gases. So if we fill out this with numbers, if we add in our values, we get 0.355 squared divided by 0.114 times 0.102, and this equals 10.8. So what do we see? We see that in this scenario, Q is less than Kp. So if we think about remember we thought about our line, and here's our K value, and here's our Q value. So we got to go this direction. So it is not at equilibrium, and the reaction will, we say, move to the right. Or in other words, more product is going to form before this reaction reaches equilibrium.